So we now kind of know that if magnetic fields interact, they cause forces, and we're going to use this to our advantage. An electric motor has the motor effect, and that is when a conductor is moved because a current passes through the conductor in a magnetic field. So this conductor over here is sitting inside this magnetic field. We've got a magnetic field from north to south. Around this conductor there's a circular magnetic field, and it is going to be going in a clockwise direction. The interaction of those two magnetic fields is going to cause movement. Now I'm going to just show you, it's difficult for them to present it in an exam in 3 dimensions, so they often are going to do something like that, and they're going to put a out over there, and it's going to go north to south, and that coming out the page will go left and right. What happens then is you land up with a cancelled magnetic field over there and a reinforced magnetic field over there, so it's nice and strong here, and therefore this wire experiences a force in that direction over there towards the top. In this case, the conductor is moved downwards. It's quite difficult to work out again because of the interaction of the magnetic field about the conductor and the field between the magnets. So as I said, in 3 dimensions, I find it very tricky to be able to actually see what's going on. But you can, and there's a left-hand rule to help you work it out, which we'll talk about in a second. And that would dictate that this particular wire would move into the page. So if you take a look here, you can actually look on this picture and you can see how we use our left hand to be able to see things. We use our first finger to point from the north to the south pole. We use our second finger to go in the direction of current, and in this case it's going from positive around towards negative. So the second finger is going in that direction, and then my thumb will point in the direction of the force that this particular conducting wire would experience. So that's how we use the left-hand motor rule. What happens is we have electrical potential energy with the assistance of a magnetic field. So I put in electricity. I need to plug in anything that's got a motor. So I put in electricity and it moves. So you can think of a fan, you can think of a hairdryer, you can think of a drill. All of those things have got a motor in it. I plug them in the wall and out comes movement, turning movement. So a motor is a turning motor. And what happens is over here we've got another example where I have got from north to south. The current is going in that direction over there. If you take your left hand and you move it, you would see that there's a force downwards. Put your second finger in the direction of the current, your first finger from north to south, you'll see that your thumb points downwards over there. Always the direction of the magnetic field, north to south, and the current is conventional current, positive to negative, not electron flow. And again, electric energy is to kinetic energy. And we use our left hand, and the rule is called Flemings Left Hand motor rule. And we, as I said, the first finger goes in the direction of field from north to south. My current is my second finger. I put them all at right angles, and that is going to be from positive to negative. And then the force comes from your thumb. Let's look at the interaction of these two magnetic fields. So this is coming out the page. If you take your right hand rule for a straight conductor and you take your right thumb and put it out the page, you will see that you get this anti-clockwise magnetic field around a straight conductor. My permanent magnetic field is going in that direction, and on the left hand side you can see you've got a reinforced magnetic field. They're all going in the same direction, so I've got lots of magnetic field. On the right hand side of this conductor I have got a cancelled out magnetic field because the red lines are coming down, the green lines are going up, and then the weakened field leaves this wire able to move with a force into there. So we get a motion of the conductor in the direction of the fields. The maximum force occurs when the current is at 90 degrees to the magnetic field. If I put the current carrying conductor in parallel to the magnetic field, I get no force whatsoever. So the maximum force that is experienced by the conductor is when the conductor is at right angles to the magnetic field, and when the conductor is parallel to the field, I do not get a force, and that's going to become important in just a second. This isn't very useful unless we can harness it into some sort of a device. So a current carrying conductor, a permanent magnetic field, I land up with a force, and that is going to move stuff. And we use this in something called the electric motor. And what we do then is we put a coil into the permanent magnetic field, and the electric current passes through the coil. And if you think about it, on this side I would experience a force. Take your left hand, point from north to south. Second finger must go, with your first finger point from north to south. Your second finger needs to go where this little red line is going over there, and you'll see your thumb points upward. On the other side, your first finger goes from north to south. Your second finger goes down with this red line, and you would see that this arm would go down. And what does that cause? If this arm's coming up and that arm's going down, this motor is turning around and around. We need something called a split ring commutator to get it to work properly, and I'll explain that in a bit more detail. But the current gets supplied, so I need to give a motor electricity. With the help of a magnetic field, I get this turning motion. And the commutator does two things. It reverses the current. So in just a minute, this arm will be on this side, and the current will be going up instead of down. This arm will be on this side, and the current will be going up instead of down. So you're going to continually be exchanging the current, and also you can see it's got a split in it. That stops the current just for a second, because at one little point in this whole thing, the coil becomes vertical, and what happens is that the force actually works against itself. It kind of jams the coil, and so you don't want that, because jamming is not good. So you actually stop the current for a split second, and then the momentum of the coil carries itself over through the coil, through that vertical position. Now we're going to take a look at how a motor works in a second. Your magnetic field is always from north to south. This thing over here is your split ring commutator. Firstly, you need to understand that these are soft brushes. In other words, that is not welded. It is a loose connection, and this thing can spin loosely whilst these two things stay fixed. These are called the brushes. That's the split in the split ring commutator over there. My current comes across from positive in around to negative, and as this turns, the blue side would be over here, and then the blue would get positive and the red would get negative, and so it turns like that. If I want to get the most movement, I use a stronger current, a stronger magnetic field, more coils on that coil, and then I need to have a maximum angle of 90 degrees between the two magnetic fields, and that gets me the best interference and the best force coming off it. Obviously, as it's turning all the time, I can't keep this all the time, but I do have my greatest force when the current flows at 90 degrees to the magnetic field. Now if we're going to watch what happens here, you can see that coil going round, and you can see how the split ring commutator is going to have a different effect. There is that moment in the vertical position where there's no contact being made at either of those points, so there's no current for a split second, and it's able to rotate through. And over here, I'm going to have my current coming from positive through. My current's going up over there. If you use your left hand, go from north to south, with your first finger, second finger going over there, you will see that this arm will be going up, and simultaneously that arm would be going downwards, and so you get this clockwise motion. And again, if I swap the north and south, notice it turns in the opposite direction. If I swap the positive and negative, it will also turn in the opposite direction. There we go. And that is how your motor moves. If you don't have the split ring commutator over here, you are not going to get, it will jam, and you will not be able to spin this motor freely round and round in circles like that. So these are the official functions of the split ring commutator. It allows for free rotation of the coil by brush connection. So it's a split ring commutator includes these brushes, It swaps the direction of current in each arm every 180 degrees, which means that the left-hand side is always going up and the right-hand side is always going down, or vice versa. And it stops the current for a split second every 180 degrees so that the coil does not jam. You need to learn those. They love asking the functions of a split ring commutator. An ammeter, you guys all know what an ammeter is. The more current that flows, the greater this motor effect is over here. So there's a little motor inside an ammeter. They increase the current flow and then the needle moves further or less. So it's a force that the needle experiences, and we see that as a reading on an ammeter. So an ammeter measures the amount of current flowing. When the current flows in the conductor between the poles of the magnet, the conductor experiences a force. The greater the current, and obviously that conductor is attached to this pointer, and the amount of movement in the conductor is determined by the amount of current. So more current and you get more movement on that ammeter.